This is the first lesson of a kinematics playlist that I'm creating. So I'm going to quickly explain what kinematics is before moving on to the video. Kinematics is a branch of physics that describes how things move without worrying about the forces causing that motion. In kinematics, reference frames and displacement are foundational topics that you can't skip. You'll build up to more advanced topics later on, like velocity and acceleration. In physics, you have to understand that any measurement of position, speed, or distance is made with respect to a frame of reference. Let's say we have a train. Here's our beautiful train. Here's his wheels. Here's his window. He's moving forward relative to the ground at 80 kilometers an hour. If somebody on the train, so a human on the train, walks forward toward the front of the train at 5 kilometers an hour, relative to the train, he's moving at 5 kilometers an hour. But relative to the ground, he's moving at 85 kilometers an hour. Because the train speed is also taken into account. I'll say that again. Relative to the train, he's walking at 5 kilometers an hour. But relative to the ground, he's moving at 85 kilometers an hour. He's moving with the train. In everyday life, we speak in the reference frame of Earth. Let's take our same beautiful train that we have created. Now he is driving forward on the ground at 100 kilometers an hour. Someone inside the train, so this guy here, he decides to throw a ball up and down. So straight up and straight down into his hand. From an outside observer, what does he see? I'll give you a second to think. He is going to see the ball move in this kind of path. A curved path. Because the ball is moving forward with the train from his perspective. But from the man on the train, he just sees the ball going straight up and down. So the important thing to remember is that motion depends on the observer's frame of reference. Moving on to displacement. Displacement and distance are not the same. You must understand this. I'll give you an example. Let's draw up a quick coordinate thing, because in physics we like to do that. You decide to go on a walk, and you walk 50 meters north. Then you turn around and you walk 20 meters south. The total distance you've traveled, so distance traveled, is 70 meters. 50 meters plus 20 meters, 70 meters. However, your displacement is 30 meters. Because the definition of displacement is how far you are from your starting position. You're 30 meters north from your starting point. So displacement is a quantity with magnitude and direction. Magnitude being 30 meters here and direction being north. We call these vectors. Vectors are quantities with magnitude and direction. Now you might have learned about vectors in math. If you haven't, it's okay. In diagrams, they're represented by arrows. So our displacement vector, here we will draw it like this on the graph. In 1D motion, which is what this whole video playlist is about, vectors can be negative or positive, because usually 1D motion is along a line. So it's either going this way or this way, negative or positive. Here it's going up and down, same thing. Now I'm going to give you the mathematical definition of displacement. Consider an object's motion over a particular time interval. So let's say at the initial time, which we'll label as t1, the object's position was x1. At some later time, so we'll call that later time t2, the object has moved to a new position, x2. Then the displacement of our object is x2 minus x1, the change in x. And we denote this in physics with the Greek symbol delta, delta x. And delta just means change in. So change in. This means change in x. I'll give you an example. So here we have x and y. Say we want to find the displacement of an object, and it traveled from 50 meters, which is our x1 position. And later, it moved all the way to 200 meters, which we'll label as x2. How do we find the displacement? And also, we're going to use vectors to represent this. So here's our beautiful arrow to represent our vector. Now let's find the displacement. Displacement is delta x, which is the final value. So final value minus the initial value. Here, the final value is 200 meters. 200 meters minus the first value, 50 meters. The displacement is 150 meters. Done. Here's a second example. Let's say you have a car, and your car, here's our car, it drives to the left from 200 meters to 50 meters. What is the displacement? So remember, displacement is x2 minus x1. Let's identify which position is x1 and which one's x2. x1 would be our first position, so our starting position, 200 meters. And it travels to 50 meters, which is our second position, x2. Let's find the displacement. So delta x is equal to x2 minus x1. x2 is 50 meters, x1 is 200 meters. So the displacement is negative 150 meters. So that's why our vector arrow is going to the left, because it's negative. And it makes sense because that's the opposite direction. Now I'll give you a quick challenge before we move on to the next example. If you were to walk 10 meters east, 5 meters west, and then another 20 meters east, what is your total distance traveled and your displacement? Hang on, let me clean up this 10 meters. It looks bad. Pause the video and figure it out. So your total distance is 10 plus 5 plus 20, which is 35 meters. That's how much you walked in total. Your displacement would be 10 minus 5, because you're walking backwards, plus 20, which is 25 meters east. In physics, it's important to give not just the magnitude, which is 25, but also the direction, so east, because displacement is a vector. Before we start today, I have to make something clear. In ordinary language, speed and velocity are synonymous, but in physics, they are distinct from one another. So what's the difference? Well, velocity is a vector, so it has magnitude and direction, but speed is just a number. It only has magnitude, no direction. And the reason why is because speed is distance over time, while velocity is displacement over time. And since displacement is a vector, that means velocity is also a vector. Let's take an example from the last lesson in this playlist, which if you didn't watch, it's okay, you can still follow along. You walk 10 meters east, you walked 5 meters west, and then you walk 20 meters east again. Let's say this journey took 20 seconds. The speed would be the total distance over time. So speed would be 35 meters over 20 seconds, which is 1.75 meters per second. However, your velocity is displacement over time. Your displacement, so how far you are from the starting position, is only 25 meters. So that means your velocity is 1.25 meters per second east. And here's something to remember. Velocity will always take the direction of your displacement. Now, let's suppose that we had an object, and at a specific point in time, so we'll say t1, the object is at the position x1. At a later time, so t2, it's moved to the position x2. The elapsed time, so change in time, which we denote with delta, is t2 minus t1. Displacement, if you remember, is delta x, so x2 minus x1. Then what's average velocity? Average velocity is denoted with v with this little line over it. This line is the standard symbol for average. So if you see a with a bar, that's average acceleration. Your textbook notation might differ slightly, but usually it's pretty similar across most physics courses. So average velocity is equal to x2 minus x1 divided by t2 minus t1. So that's delta x over delta t. Displacement divided by elapsed time. Let's see this in action. Let's use an example. Let's say you have a rolling ball and your ball starts at 8.4 centimeters at time 3 seconds. So we'll label this as t1 and this as x1. At t2, which is 6.1 seconds, your ball has rolled all the way to negative 4.2 centimeters. What is the average velocity of your rolling ball? Let's use our definition. So average velocity is delta x over delta t, which is x2 minus x1 over t2 minus t1. Let's plug everything in. So x2 is negative 4.2 centimeters, subtracted by 8.4 centimeters, which is x1. Do the same thing at the bottom, so 6.1 seconds minus 3 seconds. The average velocity is roughly equal to negative 4 centimeters per second. Here's a second example. A car drives at 50 kilometers an hour for 100 kilometers. And then the driver decides that's too slow. So he speeds up to 100 kilometers an hour for another 100 kilometers. For this entire trip, what is his average velocity? So let's solve this together. Average velocity is equal to change in x over change in time. The change in x is 200 kilometers because it's a 200 kilometer trip, as we know from this bit of information. The elapsed time, well, we're going to have to do some math to find this. So first he traveled 100 kilometers at 50 kilometers an hour. So that would be 2 hours of traveling. To travel 100 kilometers at 100 kilometers an hour, that is an extra 1 hour. So in total, he traveled for 3 hours. Do your division and it comes out to be 67 kilometers an hour. That is his average velocity for the entire trip. Before I give you your own example, I'll go through one more question. You have a cyclist and she rides her bike for 2.5 hours at an average velocity of 18 kilometers an hour. How far did she travel in this time? So we're not looking for velocity this time. It's given us the velocity. Instead, we're looking for distance or displacement. We're going to have to do some rearranging here, which is an important skill in physics. You're going to be doing this a lot in the future to find different values. If we know the formula for average velocity is delta x over delta t, we can multiply both sides by delta t, and you end up with delta x is equal to delta t times average velocity. This is the formula for displacement now. So let's go and plug everything in. Her distance is equal to the time, so 2.5 hours, multiplied by average velocity, so 18 kilometers an hour. Once you go through and solve that, it means she's traveled for 45 kilometers. Here's your own average velocity challenge, and I'm going to make it a bit tricky so that you do some thinking, but I believe that's the best way to really understand the concept. Take a hiker. Now he decides to embark on a journey up a snowy mountain. He hikes 200 meters north for 50 minutes. And then he decides to turn around and travel 150 meters south in 30 minutes. What was his average velocity during this time? I'll give you a second to pause and do it yourself. Now, regardless of if you struggled or if you found this problem easy, I'm going to walk you through it. Average velocity, as we know, is change in x and change in time. His displacement is 50 meters. And the time elapsed is 80 minutes. But see, it's meters per minute. That's a bit strange, and in physics we like to use things like meters per second, kilometers per hour. So instead of writing 80 minutes, we're going to convert it to 4,800 seconds. Do your division and it comes out to be 0.104 meters per second north. Remember, specify the direction. Velocity is a vector. Today's topic is a bit more advanced because it steps into the realm of calculus. But don't worry if you don't know any calculus. I've planned this video out in a way where you don't need to know anything. So what is instantaneous velocity? Let's imagine you have a beautiful car and you drive it for 2 hours at an average velocity of 60 kilometers an hour. That's cool. We know the average velocity, but surely during this trip you speed up and you slow down and you speed up again. How do you find your speed at one specific moment in time? That is instantaneous velocity. Give you a conceptual example. So let's draw a graph. Let's say here's your distance traveled in kilometers and here's your speed. Let's say your car, you travel, you go really fast, you slow down because there's traffic. How do you find your instantaneous velocity? We can easily find the average velocity throughout the entire trip. But we don't want average velocity. What if we wanted to see how fast we're going at this moment in the trip? The concept of instantaneous velocity is that you zoom in on an infinitesimally small time interval. And you zoom in so much that you manage to capture one instant, an infinitely small amount of time. Your average velocity in that super small time interval is your instantaneous velocity. In maths, this is called the derivative. So if you've already learned about derivatives, then this might be more intuitive. If not, it's okay. Now to expand on this concept, imagine a car speedometer. As you drive, it's going to update. It's going to change. And how is it constantly updating your speed? It has to take your instantaneous velocity right now and then update it. So that's a real world application. Now here's the mathematical definition, or I guess the formula. Your instantaneous velocity is equal to limit t approaching 0 delta x over delta t. Don't panic if you don't know limits yet. I'm going to explain this notation. This just means that you should evaluate this fraction here as t gets closer and closer to 0. So obviously, as t approaches 0, it becomes instant. And quick note, if an object moves at a constant velocity, then the average velocity is the same as the instantaneous velocity. Makes sense, right? Obviously, if the speed is changing throughout, then no, it's not the same. Today, I'm only going through one example because I believe understanding the concept is far more important than understanding how to solve these problems. So I'll give you an example and we're going to solve it together. You drive your car down a straight highway and you speed down the highway. It's really fun, but you want to find how fast you're going 2 seconds after you pressed on the gas pedal. Your car's position in meters is given by the function xt equals 5t squared plus 2t. Let's go through this together. So remember the definition. It's limit delta t approaching 0, delta x over delta t. And really quick, we have to define delta x. Delta x, we will define it as x t plus delta t minus x t. What does this mean? Now this is taken from the derivative definition, but don't worry if you don't know derivatives. So here delta t is our super small time interval that we're using. So this equation reads as x at time t plus a super small time interval subtracted by xt. And we know t is 2 seconds. We're looking for it at 2 seconds. So delta x is equal to x 2 plus delta t minus x2. Let me make some space. Velocity is equal to limit delta t approaching 0. And now here's a part where it's easy to make some mistakes, but really we're just plugging everything in. Take this, your function of x, take this and plug it into this. Our first term, so we're going to be writing this part first, is 5, 2 plus delta t squared plus 2, 2 plus delta t. There's our first term done. Now we have to plug it into this part. So I'm going to rub some stuff out, make some space. So remember, it's minus and then 5, 2 squared plus 2 times 2. And all of it is divided by delta t from up here in the definition. Now when you go ahead and expand all the brackets, solve all your things, cancel stuff out, the answer comes out to be 22 meters per second. What is acceleration? Well, the definition of acceleration is the rate of change in velocity. So imagine you're in a Lamborghini. Here's our Lamborghini. And you turn on the engine, you blast forward. The feeling that you feel as you get pulled back into your chair, that is acceleration. So acceleration is the change in speed. The mathematical definition, or the formula for acceleration, is a with a bar over it. If you remember from last video, the bar is the standard symbol for average. So average acceleration is equal to change in velocity over change in time. You might notice this is very similar to the average velocity formula, which is delta x over delta time. But this time we're using velocity up here. So this is also v2 minus v1 over t2 minus t1. Since velocity is a vector, acceleration is also a vector. Now for instantaneous acceleration, which I'm not going to touch on today, because it's basically the same thing as instantaneous velocity. Instantaneous acceleration is a equals limit delta t approaching 0, delta v over delta t. So it's the same thing as up here, but you evaluate it in the limit of delta t approaching 0. Let's do our first example for today. You're driving your Lamborghini again, and it's down a straight road. You accelerate from 0 to 75 kilometers an hour in 5 seconds. What is the magnitude of the average acceleration? Let's use the formula. A equals change in velocity over change in time. The change in velocity is 75 minus 0. So 75 kilometers an hour divided by the change in time, which is simply 5 seconds. There's a problem. We have a unit mismatch. We have seconds, kilometers, and hours. So let's use a conversion factor to convert this up here into meters per second. We're going to multiply 75 kilometers an hour by 2 conversion factors. 1 hour over 3600 seconds to get rid of the hour, and 1000 meters divided by 1 kilometer so that we can cancel out the kilometer. Do your cancelling and you end up with 75 times 10 meters per 36 seconds. Put it into a calculator, you get roughly 20.83 meters per second. So why did I add this conversion step into this problem? Well, you're going to be doing this kind of thing quite often in future physics problems. And I'm just making sure that you get some exposure to it early on. We're going to substitute our new velocity into here. This comes out to 20.83 meters per second divided by 5 seconds. Do your calculating and you get 4.17 meters per second squared. This is your acceleration. And why is it squared? Here you see meters per second over seconds. Meters per second over seconds is equal to meters per second squared. So acceleration is always in meters per second squared. If you see second squared, it's accelerating. I'm going to give you an example to solve on your own. You have a sprinter, so sprinter running a race, and he accelerates to a speed of 9 meters per second in 1.38 seconds. What is the average acceleration in meters per second squared? Go ahead, pause the video, and try to solve it. And let's solve this together now. A is delta V over delta T. The change in velocity is 9 meters per second, and the time is 1.38 seconds. This is roughly 6.52 meters per second squared. What about the opposite of acceleration? Deceleration. There's a common misconception that deceleration is always negative, but it's not always negative. And here's why. I'm going to draw a diagram to help you understand. Let's say you get our Lamborghini again, and he's moving to the left at a velocity of -5 meters per second. And the acceleration is going to the right. Well, this acceleration, because it's in the opposite direction of the velocity, it's counteracting the velocity and is therefore decelerating your Lamborghini. So even though the acceleration is going to the right, a positive direction, it's still decelerating your car because the acceleration and the velocity are in opposite directions. Here's the final example for today, and it's slightly different. Let's say you have a motorcycle and it's moving at 20 meters per second. It decelerates at a rate of 2 meters per second squared. So it's decelerating. The question is, how long does it take to come to a full stop? Well, this is going to take a little bit of rearranging. Let's take the formula for average acceleration. Delta V over delta T. If we multiply both sides by delta T, we get A T equals V. And then go ahead, divide both sides by velocity. We find that the time is equal to velocity over average acceleration. Now we can go ahead and solve for time. So T is equal to 20 from up here over 2, which is here. The time is equal to 10 seconds. So after 10 seconds of decelerating, the motorcycle comes to a complete stop. In this video, I'll teach you to use the 4 kinematic equations, which you're going to use very often later on. And they're used when acceleration is constant and unchanging. So there's 4 kinematic equations in total, and they all serve different purposes. Here's how the video is going to go. I'm going to derive the equation really quickly, and then I will go through an example. Now, the reason why I'm going to derive the equation first is because it's good to know where it came from, as in the future you might need to be rearranging them, and this knowledge is extremely fundamental. Let's start with some notation. So as you know, average velocity is delta x over delta time. This is equal to x2 minus x1 over t2 minus t1. But we're going to change the notation for these kinematic equations. We're going to use final velocity as just x by itself. Take away initial velocity, which we're going to call x0. Same with time. We're going to do t minus t0. T0 is usually numerically just 0, because imagine you have a stopwatch and you click start. It starts at 0 seconds, so we're just going to write it as 0. So our new average velocity equation is x minus x0 over time. Next step, we have average acceleration is equal to velocity minus initial velocity over time, assuming acceleration is constant. If you notice, this is in the same format as these up here. Now with this new acceleration formula, we can do some rearranging to find velocity. So let's multiply both sides by t, and we get at equals v minus initial velocity. Add v0 to both sides, and you get velocity is equal to v0 plus at. This here is the first kinematic equation. I highly recommend you write down the kinematic equations. They are absolutely everywhere in the field of mechanics. Let's run a quick example with our new equation, which, if you remember, is v equals v0 plus at. A quick note, if you see v0 here, some textbook notation, they prefer to write initial velocity as u. So if you ever see velocity equals u plus at, just remember that u is initial velocity. However, in a lot of textbooks, it's also v0. v0 makes more sense to me as the starting velocity. So that's what I'm going to use. Now imagine a skateboarder skates at 4 meters per second, and he decides to speed up at 1.5 meters per second squared for 4 seconds. What is his final velocity? So how fast is he traveling after this acceleration? Let's do it. So take this equation for final velocity. Velocity equals initial velocity, which is 4 meters per second, plus acceleration, which is 1.5, multiplied by time, which is 4 seconds. Run your calculations and you get velocity is 10 meters per second. So after this quick acceleration period, he is skating at 10 meters per second. Now for the second equation. The second equation is for average velocity. Average velocity is usually just simply delta x over delta t. But in the context of kinematics equation and constant acceleration, we can write it as v0 plus v over 2. This means the average velocity is simply halfway between the initial velocity and the final velocity. Halfway. It's the average. So here is the second kinematic equation. Now for the third equation, it's going to take a few steps. How would you find the position of x after it undergoes constant acceleration for a time t? Well, let's take our very original average velocity equation, not our new one that we created. Average velocity is displacement over time. Let's solve for x. So multiply both sides by t, you get vt equals x minus x0. Add x0 to both sides, and you end up with x equals x0 plus vt. The next step is to plug in our second kinematic equation, which we just derived, which is v0 plus v over 2. We're going to plug this guy in right here. So that gives us x equals x0 plus velocity 0 plus v over 2 times t. Pay close attention here. We're going to plug in one more equation. I know it's a lot, but here. See this velocity. If you remember our first kinematic equation, velocity equals velocity 0 plus at. We're going to plug that in now. So that becomes v0 plus v0 plus at multiplied by time. Next, we're going to expand this bracket, and this is our third equation. X equals x0 plus v0t plus 1 over 2 at squared. This is kinematic equation number 3. Make sure you write this one down because this one, I see it everywhere. It's used very, very often. Now for the final equation. It's useful in situations where time is unknown, but you want to find things like velocity and displacement. This final equation does that. Now let's take this equation for x. Here we can plug in the second kinematic equation. So let's do that. We get x equals x0 plus v0 plus v over 2 times t. Now how's this going to help us solve stuff when t is unknown? T is still in the equation. Well, let's fix that. Take the first kinematic equation and rearrange it for t. First, minus velocity from both sides. Then divide by acceleration. Then you end up with time equals velocity over acceleration. We're going to plug this in here. So now we end up with this juicy big equation. Expand this stuff and you end up with x equals x0 plus velocity squared minus initial velocity squared divided by 2a. Now this isn't quite the final kinematic equation. If you went and rearranged the equation and solved for velocity squared, it would end up as velocity squared equals initial velocity squared plus 2a displacement. This is the final kinematic equation, and it's used when you don't know time, but you have stuff to solve. Now, really quickly, take a look at this equation. Let's subtract x0 from both sides. This becomes x minus x0 equals velocity squared minus v20 over 2a. This right here is a variation of this equation. However, it finds displacement instead of velocity. Here is a quick recap of every equation. First, we have the velocity equation, then the displacement equation, the velocity equation when you don't know time, and the average velocity equation. Please understand this. These equations are not valid. They do not work if acceleration is not constant. So these kinematic equations, these four equations, they only work when acceleration is uniform and unchanging. And remember, depending on your textbook notation, or maybe you're taking a course at school, depending on the course notation, sometimes initial velocity is u, and displacement is sometimes d or s. So keep that in mind. Okay, let's do some fun examples now so that the concepts can click for you. So you have a small plane, and to take off the ground, it needs to reach a velocity of 50 meters per second. Plane on the runway accelerates at 3 meters per second. The question is, how far does it have to travel to reach this takeoff velocity? First, let's identify what exactly we're looking for. We're looking for the length of runway required for the plane to reach this takeoff position. So basically, displacement. Now flip back through your notes. Which equation gives you the displacement? The equation is x equals initial position plus initial velocity time plus 1 over 2 acceleration time squared. Let's identify our variables. So initial position, we can just write as 0. The initial velocity, since it's starting from rest, it's also 0. Now the acceleration is 3. And it seems we're missing something. We don't know the time. We don't know how long it takes. So let's take a step back and quickly solve for time. Let's use the first equation this time. So velocity equals VO plus AT. Let's rearrange the equation for time. So T equals V minus V0 over A. Now let's plug things in. The velocity is 50, so 50 over 3, which is roughly 16.67 seconds. So the time needed to reach takeoff speed is 16 seconds. Let's plug that in here. So 16.67 seconds. Run the calculations and x comes out to be roughly 416.83 meters. So if you were to design a runway for this airplane, how long would you do it? Well, me personally, I would give it a good 450 meters of space to take off comfortably. Now I'm going to give you your own problem to try and solve. Get ready to do some thinking. So we have a bike, and it starts at rest and accelerates at 2 meters per second squared for 5 seconds. And then it travels at a constant speed, for another 3 seconds. The questions: find the velocity after 5 seconds. So this quick acceleration phase here. And the second question I give you is total distance after the entire 8 seconds. Pause the video, go ahead. Now let's solve it together. So the final velocity after this acceleration phase, we're going to use the first kinematic equation. So velocity equals initial velocity plus AT. This is equal to 10 meters per second. So after 5 seconds, he's moving at 10 meters per second. The second part of the equation is the total distance. So we're going to use the kinematic equation, x equals x0 plus v0t plus 1 over 2 at squared. The initial position and initial velocity, a lot of the time in textbooks and problems, they are completely skipped over because majority of the time there's 0. So if you ever see just this, then understand that it's because the initial position and velocity are 0. Let's plug in our values. X is equal to 1, 2, 2 times 5. So that is equal to 25 meters. So after 8 seconds, the bike moved 25 meters. The final example I'll go through today is important. This example will teach you how to find velocity when you don't know the time. So here's the problem. You have a Ferrari. Here's your beautiful Ferrari. It starts from rest and then it accelerates at 3 meters per second squared. And it does this for 75 meters. The question is, what is the final velocity of the Ferrari? And the second part of the question, as a bonus, is how long did it take? So the equation that we use when t is unknown is v squared, initial v squared, plus 2a x minus x0. Let's plug it all in. So since the Ferrari starts at rest, the initial velocity is 0. The acceleration is 3 and the displacement is 75 meters, which we get from here and here. Go ahead and solve it. You get velocity squared is 450. So velocity is root 450. Put it into a calculator and it's 21.2 meters per second. That is the velocity of the Ferrari after this acceleration period without knowing the time. Now let's tackle the second part of the problem. How do you find the time taken? Well, it's easier now that we know the velocity. Now, if you rearrange the average velocity equation to solve for time, you get t equals x minus x0 over average velocity. And you might think, oh, we can just plug this in. No, we can't, because this is the final velocity. So let's find the average velocity. Remember, when acceleration is constant, the average velocity is halfway between the starting velocity and the finishing velocity. So v minus v0 over 2, which is 10.6 meters per second. If you notice, it's half of the final velocity. So 10.6 meters squared, we're going to plug this in here. We're also going to plug in the displacement. And the answer is 7.08 seconds. So the Ferrari, after accelerating for 75 meters, is moving at 21.2 meters a second. The time it takes to accelerate to that speed is 7.08 seconds. Let me ask you a question. If you dropped a bowling ball and a feather from the same height with no air resistance, what happens? Does the bowling ball fall faster? Does the feather fall really slow? Well, let me tell you. In the 1600s, Galileo discovered that in the absence of air or other resistance, all objects, light or heavy, fall the same. With air resistance, a bowling ball and a feather would obviously fall at very different rates. The ball would obviously fall much faster. But in the absence of air resistance, so in a vacuum with no air at all, the paper and the bowling ball actually fall at the same speed. It feels weird, but that is how it works. So what Galileo discovered is that the speed of a falling object is not proportionate to its mass. And we write this as d is proportional to time squared. D being distance and t being time. And this weird little symbol just means proportional. However, this only applies with the same constant acceleration. So if the acceleration is changing throughout the course of the free-falling object, then no, this doesn't apply. Now there's something on Earth called g, and it is the acceleration due to gravity. G is usually 9.80 meters per second squared. Sometimes some textbooks will say 9.81, but that depends on things like altitude and things. So 9.80 is just fine. Let's go over an example. So imagine a bridge. Here's our bridge. A clumsy construction worker standing on the bridge drops a bolt and the bolt falls. The question is, where is the bolt after 1 second, 2 seconds, and 3 seconds. Let's solve this together. We're going to use the kinematic equation for displacement, which is x equals x0 plus VOT plus 1 over 2 AT squared. We're going to label the bridge as y equals 0. And as you fall, y is increasing. That's our frame of reference. Instead of x, let's write y. Starting x is 0. And starting velocity is also 0. And the reason why we know it's 0 is because the way this problem was worded. He dropped the bolt, so it starts from 0. If he threw the bolt down, then there would be an initial velocity. Since he only dropped it, it's 0 plus 1 over 2. Now here we're going to plug in g, which if you remember is 9.80 meters per second, and time squared. So let's go and plug in 1, 2, and 3 for time squared. At 1 second, y is equal to 4.9 meters. So the bolt falls 4.9 meters at 1 second. At 2 seconds, when you plug in 2, the bolt has fallen 19.6 meters, which is quite a bit more further. At 3 seconds, then the bolt has already fallen 44.1 meters. So this is 1 second, 2 second, 3 second. Now, what if it was the exact same bridge? However, instead of dropping the bolt, the guy threw the bolt down at an initial velocity of 5 meters per second. If the bridge is 40 meters tall, so 40 meters tall, from the water down below, 1, how long does it take to hit the water? And 2, the velocity after hitting the water. Let's go ahead and solve this. Let's use the same equation because we're still looking for displacement. We're going to go and plug everything in. Now, final position is actually 0 here because 0 meters at the bottom of the bridge. 0 meters, the starting position is 40 meters. So 40 meters plus the starting velocity, which this time exists, it's 5 meters per second. Multiplied by time plus 1 over 2, 9.80 times time squared. When you go through and expand all of this, you get 4.9 T2 plus 5T minus 40 equals 0. This is a quadratic. So if you run it through the quadratic formula and solve for T, which would be this, then you would end up with the answer for T. So I'm not going to do that on camera because that's going to take forever. But T, the answer is either 2.39 seconds or negative 3.41 seconds. You might say negative time? That's not possible. That's very weird. So that doesn't exist and it's not real. So we're going to discard that answer. We're not going to use it. We're going to ignore it. The answer that actually works in real life, 2.39 seconds, we will gladly take. Now that we know that time is 2.39 seconds, we can go and find the velocity after it hits the water. So when the bolt hits the water, the velocity is equal to VO plus AT. Remember, the starting velocity is 5 meters per second. Acceleration, 9.80. And the time from here is 2.39. The velocity after the bolt hits the water is roughly 28.42 meters per second, downwards. Moving on to the final example, which is a bit more complicated, but it's also a lot more fun. Let's say you have a really big rocket and you launched the rocket off the ground with an initial velocity of 500 meters per second. 1. Find the maximum height of the rocket before it starts descending. And 2. Find the total time it took for the entire trip, so up and down. So we know the initial velocity, which is VO, is 500 meters per second. Since the time it takes to reach maximum height is unknown, we're not going to use the displacement equation. Instead, we're going to use this one, v squared equals v squared 0 plus 2a x minus x0. Rearrange it for displacement, you get x minus x0 equals v squared minus v squared 0 over 2a. We've used this in the previous video on kinematic equations, so you might have seen this already. Now let's identify our variables and plug. So we already know the initial velocity. Now we need the final velocity, so the velocity at the peak of the trip. The final velocity at the peak is going to be 0. Why it's 0? Because, well, when you're flying up and up and up, you're going to pause for one tiny instant, and that tiny instant, your velocity is 0 before you start falling down again. We know acceleration is negative 9.8 because that is the gravitational acceleration downwards. And x, well, that's what we're looking for. Plug everything in, you get negative 500 squared over negative 9.8 times 2. Put this in your calculator, and you end up with x is roughly 12,755.1 meters. So that's how high the rocket flies up before falling down again. The next part of the question, if you remember, is how long does the entire trip take? So this part, there's actually multiple ways to approach it, but I'm going to teach you the most efficient way, which is important because that means you're less likely to make mistakes. Let's draw our diagram. This can be point A, which is where we start. And here is point C, where we land. The rocket flies up and up and up and up, and then turns around, starts floating down. We're going to call the peak point B. Here's what's happening. On the way up, we have our velocity pushing us and gravity pulling us down. On the way down, our velocity is going down and our gravity is going down. So remember, the original question is how long it's in the air before landing. We could split this equation into two parts, finding how long it takes to go up and how long it takes to go down, but we don't want to do that. That overcomplicates it. Instead, we can just consider this entire time interval from A to B to C. So remember, we're looking for time. Let's find time. If we take the displacement kinematic equation and plug everything in, so initial velocity plus 1 over 2 negative 9.8 times t2. Now, the final position is actually 0 because it ends up back on the ground. That's the final position. If you go ahead and rearrange everything here, you can end up with 0 equals 500t minus 4.9 t squared. If you factor out t, you get t 500 minus 4.9 t equals 0. This is a quadratic. That means t is equal to either 0 or negative 500 over negative 4.9, which is roughly 102.04 seconds. There we go. Here's our two answers for seconds. But which one's correct? Well, in the last example, when we had two answers from a quadratic, we just threw away one of them because it wasn't real. This one, both of these are actually valid. T equals 0 seconds. Well, that's referring to A at the very start of the trip. It's been 0 seconds. This is after the entire trip, and you land at point C. It's been 102 seconds. Welcome to graphical analysis of linear motion, which is the last topic to cover in 1D kinematics. When you analyze a graph of linear motion, it will give you additional insight into kinematics. So let's start with an example. Take a position time graph. So a position time graph means that it relates position, which will do m, and time, which will do seconds. Now imagine this graph had a line go through. Let's label some points. Let's say this is T1, this is T2. This is x1 and this is x2. These points, when you look at the graph and the line, you recognize that it creates a triangle here. So if this is x2 minus x1, which is the change in x, and this is t2 minus t1, which is a change in time, then the slope of this graph, this position time graph, is delta x over delta t, because rise over run. And you might recognize this. This is average velocity. So the average velocity of a position time graph is the slope. If this change in x, let's say, was 11 meters and this movement in t was 10 seconds, then it would be 11 meters over 10 seconds, which is 11 meters per second. Let's take another graph. And this time, it's still a position time graph, just like before. So this would be t, this is x. Now this time our graph looks like this. This is our t1 and our x1. This is our t2 and our x2. As you can see, it still makes that same triangle as before, with this side being delta x and this side being delta t. But let's name these points. This point here will be P1, so x1, t1. This point here will be P2, so x2, t2. So we've just labeled these 2 points. The slope of P1, P2, as we learned from the prior example, is delta x, which is also the average velocity during this time interval, delta t. Why am I telling you this? Well, this means that the average velocity of any time interval, delta t, is the slope or the chord line connecting these 2 points. So here's a curve and everything, and it might look like that. But if you draw a straight line between these 2 points, the slope of that line is still the velocity here during this time interval. Now here's the same graph, but I'm going to explain a bit more of a complex example. So I'm going to explain what the tangent line is. Now, you might have learned the tangent line in math. If not, it's okay. I'm not going to spend too much time on this because this is stepping into the realm of calculus. So let's take this point here. The tangent line to this point would be a line that barely just touches it for one tiny instant. This is called the derivative, or instantaneous velocity. And the reason is, well, take this thing here. If you zoom in, so right now it looks something like this, right? When you zoom in enough, the lines both become straight, which means that the slope of the tangent line is the slope of the curve at time t. Now I've just talked a lot about random theoretical things. Now we're going to apply this to a problem. So take a graph, which I'm going to draw really quickly. Okay, here's our graph. This is not a position time graph. This is a velocity time graph. Now the graph is going to describe the motion of 2 Ferraris. Ferrari number 1 will drive like this. Ferrari number 2 will drive like this. This will be Ferrari B, that's what we'll call it. And this will be Ferrari A. Here are the questions. First, compare the average accelerations between the 2 cars. 2. Analyze the instant acceleration between the 2 cars. Finally, compare the distance of the 2 cars. So let's start with the average acceleration. The average acceleration is velocity over time. And here we can see that this here is the change in velocity and this here is the change in time. So that means the slope is the acceleration. If you think about it, both cars actually have the same average velocity and the same time, because they both travel for 10 seconds and they both reach the same spot. So they actually have the same average velocity, which is 100, which you take from here, 100 kilometers an hour over 10 seconds. So that's the average acceleration. It's the exact same for both cars. Second problem, the instant acceleration. Compare them. So here you can see from 0 to 4 seconds, car A is clearly steeper than car B. So we can say that from 0 to 4 seconds, A is faster and accelerating faster. However, from 6 seconds to 10 seconds, this time interval, B starts to get steeper and catch up to A. So we can safely say that from 6 to 10 seconds, car B is accelerating faster. Now for the final problem, which is comparing the distance traveled for both cars. Now we have to do some creative thinking. But if you look at it, Ferrari A is always going faster. It always has more velocity than Ferrari B, even if they both ended up at 100 kilometers an hour in 10 seconds. Because Ferrari A's velocity is always higher, then that means Ferrari A is guaranteed to have traveled further than Ferrari B in the same amount of time.